So I think this was some result we used in something the other day. I can't remember the exact question. Just that the what was it? Like revision session, showing that if we've got a standard normal random variable, that the expectation of the fourth moment is 3. So how do we prove that? Well, from Taylor's theorem, from hopefully sort of first year calculus when you learned that. In terms of the conditions for Taylor's theorem, I don't care about a particularly precise statement here, but certainly if the function has an infinite number of, if all the derivatives of f exist, then we can expand the function of p as follows in the usual way. And I'm just ignoring, the higher order terms here with the dot, dot, dot. For our purposes here, we need to go to fourth order. So the particular term that we'll be looking at is this, so it's 1 over 4 factorial p to the 4 and the fourth derivative of the function f here, but evaluated at 0. Hopefully you're familiar with this kind of thing, although we don't usually have to go to fourth order, but we do for this particular question. Then, of course, the well-known example when fp is equal to e to the p, we get, I knew there'd be something, that there were these z's that it turns out I didn't need. So, forget about that z. So, so you're hopefully familiar with the Taylor series of the exponential function. Now, it turns out I only need to write this out to second order. So I've ignored the higher order terms because my interest then is in replacing p. If this is true, then it's also true that this is true. So I'm now replacing p by a half p squared. So, of course, that p gets replaced by half p squared, and that gets replaced by half p squared, which comes to an 8th p to the 4. So, so if we then compare, this is the general Taylor series, and this is the particular Taylor series of this function. So, so what function are we considering now? I mean, we're now considering, I should have written this really, but e to the half p squared, because I originally had this function, but then I replaced p with a half p squared. So what I want to know is what is f prime, i.e. f dash 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 dash. Did I say that? F dash 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 dash. Yeah, fourth derivative of f at 0. So if we compare, so all we have to do is compare the p to the 4 term there and the p to the 4 term there. And when we do that, we see that we get 1 over 4 factorial f, 4 times the 4th derivative of f at 0 is equal to an 8th, because that an 8th is in front of p to the 4 there. And here you've got 1 over 4 factorial times f prime of 0. So that tells us that f prime 0 is 3. So this is already telling us something about where the 3 comes from, but we need to just finish the proof. So I did have something here, and I've broken it into 2 lines because otherwise it got rather confusing about the order in which to do things. So we first of all have the general observation that we mentioned in the very first lecture, the applied revision lecture, that, well, in this particular case, we're interested in the fourth derivative. So if we take for any random variable, well, as long as this is well behaved, and we'll talk more about that in question 2. If we take the fourth derivative and assume we can take this derivative inside the expectation, when we do that, and then also evaluate at p equals 0, you clearly get e to the z to the 4 here. But that's a general result. It doesn't really use anything particularly about our normal random variable here. But then if we then use the fact that we also know that for our normal random variable, the moment generating function is a half p squared, then for our particular example here, this fourth derivative here, this is just the same as what's here, but is also the fourth derivative, is the fourth derivative of e to the half p squared, but we've already shown that this is 3. So this shows that that and that are the same expression, but this was a way of rewriting this expression in general, but this was the calculation that applied to our particular normal random variable for this particular question. So this shows that this and that are actually equal to each other. Okay, so yeah, that's the end of that question. And then, so it occurred to me, so once again there, I was assuming this whole thing of taking a derivative inside an expectation. I've kind of done that too many times without justifying it. So I thought, okay, I looked up the proof of how you actually do that, and it was different to how I thought actually, but it's quite a nice little proof. So we'll look at that now. So it says, consider a non-negative random variable x for which the expectation of e to the px is less than infinity for p in some open interval p understar to p star. So I mean, this is often the case for random variables. So yeah, so as I said, p star is less than 0, is less than p star. So you can think of this p understar and p plus as critical moments, if you like. And then it's a show rigorously result that we've used many times. So I'm just concentrating on the first derivative here. That if, because we can always repeat the result, that if we have take the derivative of the moment generating function of this random variable, which at the moment, for simplicity, because it makes the proof easier, I'm assuming that the random variable is non-negative. Show that we can d with dp of this is equal to e to the x, which, as I said, comes from essentially assuming we can take it inside the expectation, differentiating then e to the px with respect to p, which, as we've noticed before, if you perform that derivative, you of course get x e to the p of x, but there, which isn't that useful in itself. But then when you set p equals 0, you get what you want, namely, the expectation. So yeah, so it uses something called Fubini's theorem from FMO1, which essentially gives a condition on when you can interchange integrals. Have you discussed Fubini's theorem in FMO1?
Not yet, I don't think.
Okay. Yeah, it doesn't really matter. Yeah, it just says that if you if you've got an integram which is non-negative, so in this case, yeah, well, what we'll be interested in is the integral from 0 to p, and then, well, why is this a double integral? Well, because you've also got an expectation here, but hopefully you've at least seen in FMO1 that you can view an expectation of x as an integral of x dp. I assume Marcus is using this kind of notation, is he? Or, I don't know, x of omega p, like that. Has Marcus been writing things like that?
Yes.
Yeah, okay, good. Yeah, so yeah, I mean, hasn't been simplified too much, of course. Yeah, so I'm saying that, yeah, I'm just saying that, so you can, as long as you've done FMO1, which hopefully you have, you can think of this thing here also as an integral, if you like, even though we don't usually have to think about this way of thinking of things on this course. But Fubini's theorem says that we can interchange two integrals if the thing on the inside is non-negative. Which it is here, because I've just cheated and I've said let's assume the random variable is non-negative, and of course this exponential is non-negative, so we can do that. So I'm not proving Fubini's theorem here. That's not a trivial thing. Probably take an hour to do that, but that's what I'm using. And as I said, if you wanted to think of this as a double integral, as I said, it's a bit FMO1-y, but yeah, then it would be the integral from 0 to p of the integral of x e to the q x. Yeah, using this kind of notation. Although, as I say, we don't actually need this notation for this course, but dp dq. But that's why I'm saying that we can view this as a double integral. Yeah, if you want to be geeky about it. So yeah, the outer integral is an integral with respect to the Lebesgue measure, and then the inner integral is an integral with respect to the measure dp. But don't worry too much about it. All I'm saying is that we can interchange the integral here and the expectation there if this thing is non-negative. So then when we do, then we can just evaluate this integral inside the expectation as so that's a good point. I just need to remind myself to finish the FMO2 exam today, so I'm just sending myself an email. But so we can so what have I done here? So we have an integral here of the function x e to the qx with respect to q. So when you So it's easier to probably look at the right hand side. So if you differentiate e to the qx with respect to q, you get back to this. So this is the indefinite integral of this with respect to this dummy variable q. But then when you evaluate this, as we do with integrals in the usual way, at q equals p as the upper range of integration, and then q equals 0 as the lower range, you just get e to the px minus 1. So this maybe looks like a slightly strange integral to you because the x is random, but the dummy variable of integration is not random. It's just, I'm just calling it q, and the upper range is the p value that we actually care about. So what we've shown then is that this is equal to this. But then, so I say, okay, by inspection of the left-hand side, well, we see that the integral of what is here is given by this. So let's differentiate this with respect to p. So if we differentiate it in a minute, so I put a d by dp here, then the fundamental theorem of calculus is, if you integrate something and then differentiate again, this and that, those two operators obviously cancel each other out because they're the opposite of each other. So you get back to, if you do that, then you get back to just the inside, but evaluated at p. So e to the px. But then on the right hand side, we can do that as well. Yeah, that's all right. Yeah, so I was just checking that on the right hand side, I don't want to be cheating and then taking d by dp inside the exponential, or else that would be using what I'm trying to prove. So on the right hand side, I simply, well, the derivative of the 1 is 0. There's no contribution from that, but we also have the d by dp of the expectation of e to the p of x. So, and that's it then. Yeah, because that, we were trying to show that is equal to that. Granted, okay, so in case you can't see this, that's the expectation of x to the p, and that's precisely what we were asked to prove. So, is it? Oh, okay. Sorry. Well, yeah. Finally, we just need to evaluate at p equals 0. Although, I mean, it's another result. Before you evaluate, it's a more general result that in that we're usually interested in the case when we evaluate at p equals 0. So. Yeah, I don't know why I should have really said P0, not Q. Yeah. So that was I was quite surprised. That's quite a nice proof that I thought they would do it using a finite difference type argument, which I've used in the past for these kind of arguments. But it was surprising to me that Fubini is actually the way to approach it. So I won't go into details now. But yeah, if you want to extend to any real value roundabout, obviously many times we don't deal with a non-negative roundabout. A normal roundabout is of course not non-negative, i.e. it can go negative. You have to check that it doesn't matter which way round you go, whichever way is convenient, but you have to look at the double integral, but you have to take the absolute value now of the thing, of the integrand, and verify that is less than infinity. If that's true, then you can still justify Fubini. So I mean, I could rewrite the question with this condition, but I think actually I could probably give it a simpler condition that implies this condition, but I didn't want to. It would kind of detract from the one line beauty of this solution, I think, to do that. But if you have any interest in that, send me an email or something. But just to say, yeah, you could say so. The version of Fubini's that I mentioned here is actually a one special simpler case of Fubini when you've only got a non-negative integrand. But in more generality, yeah. So I mean, with what we're doing here, so you would have an integral over R, another integral of say a random variable, say dp, and it's dq in this particular case, isn't it? So I'm saying that for Fubini, you would need that to be less than infinity. And you can choose which way round you want to verify that this isn't. Once it's true at least one way round, then it's true the other way around, and you can interchange. But don't worry too much about it, or if you care, you can look that up in on FMO1 or Wikipedia or something. But so anyway, so back to your favorite topic now, barrier options. So what does it say? So write down an integral expression for the price of a. So this was a interesting one. So yeah, it's a double time window barrier option which pays 1 at time 2 if S stays So S has to stay above a lower barrier L over the first time interval from 0 to t, and then over the final part from t to t2, it has to stay below B. So if I can maybe draw what's going on here. My pen gone? No. It's weird. Am I using the wrong? Let me just plug the pen in. Oh, that's it, yeah. That's a bit straight. Yeah, it doesn't really matter. It just means I can't get a straight line. But yeah. Okay, yeah. So what I'm saying, so we've got an upper barrier, which was so it's L and B, isn't it? Yeah. Because here's my lower barrier. Here's my upper barrier. Here's my final time T2. Here's my intermediate time T1. And then I'm saying that, yeah, if the stock doesn't hit this lower barrier over the first time rule and also steers clear of the upper barrier over the second time interval, then what does it make? I think it just pays 1. Yeah, it pays 1. So in terms of when these barriers are active, this is active over that period and that is active over that. So because we've got 2 barriers, an upper barrier and a lower barrier now, this is known as a time window barrier option. And I can't remember if I mentioned before, but yeah, when I did an internship at HSBC in like 2003, I don't know, were some of you even born then? I don't know. A lot of the internship was spent pricing these things, so they do care about them in practice. So how do we price these things? So it's similar to question 2 from skills session 7. I assume that was last week. I can't quite remember. What is wrong with? Oh, goodness, it's really playing up there. Maybe I need to charge the pen. Yeah, okay. The price of the time window barrier. God, and that doesn't work. Yeah, okay. Is given. Yeah, so it's this idea of conditioning, really. So what you do, you first condition on where the stock is at the intermediate time. So it wasn't T1, it was just T is the intermediate time. That is weird. Yeah, okay, I'm not going to be able to fix that now, but yeah, that's just T anyway. The intermediate time is here. So what we first care about is the density of the stock price along this line, essentially, and that is denoted, as I often do, as this. So P of ST, and although there's no strike in this question, I've used stupid. Yeah, okay. I'm going to change the. Yeah, all right. Okay. Yeah, I've got to change one variable, although so I need to make a choice about that. It's probably easier to call that S than yeah. All right. So yeah, okay. If I use S as my, I need to make a choice about my choice of dummy variable. It's probably more because there's no strike in this question. It's probably stupid to use K. So still doesn't work. Yeah. So here's my density of the stock price at the intermediate time. And as I've said many times before, there is a formula for this in the notes, but I don't generally care about the formula so much. It's the log normal density, but you can look that up if you want to know. Once you've conditioned on where you are at this time, you then compute the. So we're always pricing options, so we're always working under Q. So what we then care about is the probability under Q that the minimum stock price at T. So it's T, not T1, isn't it? Okay. God, okay, goodness, drive me insane today. Yeah, all right. Just ST. So the minimum stock price at the intermediate time T is greater than B. No, but you may have forgotten, but we did compute the product of this times that in a previous homework question, although as in that question I think I replaced the S there by K, but that's just a choice of dummy variable. That's why I have K there. But so yeah, so in question 2 skills session 7 we showed that maybe I should, yeah, all right, so I've got K there as well. Yeah, maybe I should change that to K then, shouldn't I? Yeah, sometimes it's just a bit of a jack in the box thing of, you change one variable, you have to change another variable. So, all right, so given the stuff that's written below, easier to work with K, I think. So That's the density evaluated at the dummy variable K. That's Q of the minimum stock price exceeding B, given that the stock price is equal to K, which may look weird, but we've actually computed that before. And then we've also got K there. So if we're doing that, then this has to be a K, not an S. I'll clean that up after the lecture. But so, yeah, so the point I was getting at, yeah, in that previous course, we showed that this product of this conditional probability times this density was minus dBdK of this thing. You may remember that we used a kind of finite difference argument of considering two different K values and then letting them tend to each other and dividing by delta, which is the difference between the K. That's the argument. I think I may have forgotten in that previous question to put the minus sign there, so I've updated that previous question as well, so you might want to go back and look at that. So what I'm saying is we have a method for computing this product times this product. Again, let me just see if I can just get rid of that so I don't even need that. So okay. Yeah. So anyway, yeah. So we have a way of doing that. Blah blah blah. And then what else do we need? So the only other thing we need to talk about is the final term, which is So what are we doing here? So we first, as I said, condition on where we end up at this time, and we're using the dummy variable K to represent where we end up. K isn't really a strike variable; it's just a dummy variable. We then condition on once you know where you are along this line. What's the probability that you steer clear of the barrier, or that the minimum does not hit the barrier, given that we end up at this point? That's what we've computed here. But then finally, even when you're here, you're then interested in the probability that you don't hit this barrier. So we then just simply need to multiply what we already have by this final bit here. And then what do we want to say about that? Yeah, okay, so it's here. Yeah, so the final term is just the price of an up and out no touch at time 2, and we've already have a formula in skills session 7 question 2 for that case. So that's just once we get to what kind of option does this become once you're at the intermediate time? Well, once you get to T, there's only a single barrier which is relevant. So the time winner barrier kind of simplifies to just a no touch option, but we've already priced that no touch option. So we're really building this solution out of things we've calculated in 2 previous homework questions, which I know can be confusing. Probably, in the exam I wouldn't give you something quite this complicated, but I'm just trying to give you some practice at thinking about this stuff, because obviously I don't expect you to remember multiple homework. Well, I mean, as best you can, but I have to be reasonable about it. But so yeah, the point is to say that times that was computed in 1 previous homework question, this one, and then this which is just the price of an up and out no touch option. We gave a specific formula in another question. So was there anything else to say about it? And okay, the only other thing to say was, I've said that this product here can be computed in terms of this, but how do we get a formula for this? Well, this requires taking dBdK of this, but the expectation here can be computed in terms of static hedging argument. So, that's using something from another homework. So I agree that, it's all been built up bit by bit. So this isn't exactly a trivial expression, but we've broken it down into things that we have already computed. But I mean, it's okay just to write this line and even forget about, not talk about the specific formula. Well, it depends on what I ask in the question, but it's at least, if you can understand this line, even if you forget where the formula comes, how you'd actually calculate the formula for this and the formula for that, that's at least a huge breakthrough at your level. But so anyway, so that's the end of the homework. So does anyone have any questions about that? Yeah. So maybe I can just clean that up now. If you just give yourself a break for 2 minutes while I resend that over in a cleaned up version. So what should I'll just edit the actual source file and re-email it to myself. DK, so that I don't have to have the costings out everywhere. So fix that. I don't think there's anything else to fix. Yeah, so I've fixed that now. I'll email it back to myself. homework6 solutions. Send. Okay, go to my email. Open this one. Since there's a second version of it, open in GoodNotes. Yeah, so this should be all right now. So should have done this in the previous lectures, yeah. But yeah, so DK was the dummy variable I've decided to use here because it's consistent with everything I wrote down here. So so I'm conditioning on S2 equals K there. I'm evaluating this density at K, and I'm conditioning on S2 equals K there. And of course, I have the K here. And let me just redo the drawing for you. I assume this still isn't going to work. Oh, it's back. Okay, that's weird. Okay. While it's doing that, then yeah. So yeah, good. So something good came out of that. So yeah, there's my barrier, and there's my other barrier. That barrier is L. That barrier is B. Here's S0. Here's T, and there's T2. And as we said, this thing pays 1, which if we don't hit that barrier and then we don't hit that barrier, if that happens, then we make 1 exclamation mark. And so the other thing I said was that, yes, once we get to this point, the thing just becomes an up and out no touch because this lower barrier then ceases to be relevant. And we've exploited that in the solution here because this part here is just simply the price. Remember, S bar T is the maximum. So this is the probability on the Q that the maximum stop price stays below B at the final time, given that we're currently at K. And then the way to think about this whole expression is that we are first conditioning on where we are at this intermediate time. We then can multiply, the density of that times the probability that we didn't hit this barrier in the meantime, and then we multiply that by that. So, I mean, conceptually, it's kind of like, I don't know, writing probability of A intersection B, as probability of A times probability of B given A. It's just, it's the same idea as that, but it's just because we're dealing with continuous random variables, the thing is an integral. And I think I forgot to say that the range of integration is only from L to B, because of course, if I'm considering the stock price being here at time 2, to get to there, we must hit the barrier, in which case the option is worthless, and therefore there won't be any contribution to the price of this option. And if I wanted to, I could replace the payoff of simply 1 with something like a European call option payoff if you don't hit the barrier, in which case you would need a different pricing function here. It would be the price of an up and out European call option once you get to the intermediate time. Yeah. So that, yeah, I mean, I don't think I'll be giving you any, I guess I need to give you some mock exam questions actually, but I don't think there'll be any harder barrier option questions than that. So, but let me know, if you're struggling with that, that's what I'm here for here. So, and so any other general questions about the homework or? Okay, so I'll put that on, I think it's on Keats anyway, but yeah, this updated version on Keats, and hopefully the recording will work this time, and if it does, then I'll put the video up as well. And otherwise, I'll see you all next week. What is it? Monday, I think, isn't it? Yeah. So I'll stop the recording now.